Hi, welcome back. In this video, we're going to look at properties of determinants and how those properties can help us determine whether or not a matrix has an inverse. So we're going to start out by listing those properties in Theorem 15. We're going to let A and B be n by n matrices, and K is a scalar value in R. And we're going to list out 4 properties of the determinant. So first, if I want to find the determinant of Ka, that's going to equal K to the n times the determinant of A. Now this is a little bit strange, but we're going to talk about this one after we list all of the properties about why we end up with K to the n instead of just K. For our second property, suppose I want to find the determinant of the product AB. Good news here, that's the same as the determinant of A times the determinant of B. So if I want to find the determinant of a product, I can just find the product of the determinants, easy peasy. Number 3, if I'd like to find the determinant of the transpose of a matrix, why, that's just the same as the determinant of the matrix. And this kind of makes sense based off of our definition for determinant, because we can go along a row or a column with our cofactor expansion. And so if you transpose the matrix, the only thing you would have to worry about is that -1 to the I plus j power, because all the columns and rows are going to stay the same. But it turns out when you do that transpose, if the I plus j was even, it's going to remain even. And if it was odd, it's going to remain odd. So that's why we're going to have no change here between the determinant of a matrix and the determinant of its transpose. And our fourth property is a little bit more long-winded. It says, if A inverse exists, then the determinant of A is not 0, and the determinant of A inverse is equal to 1 over the determinant of A. So number 4 is actually giving us 2 helpful pieces of information. It's telling us that if I know that I have an invertible matrix, then I can find its determinant just by taking the reciprocal of the determinant of the matrix. It's also telling us that if the determinant is 0, then I'm not an invertible matrix. So here, our determinant, property 4, is what's giving us one of the links between determinants and inverses. If the determinant of a matrix is 0, then that means it's not invertible. If it isn't 0, that means it is invertible. So we're going to do some examples of these 4 properties here, but I want to talk a little bit about property 1 first, because it kind of links back to some of the theorems we looked at before. So let's investigate number 1 to begin with. Okay, so for example 49, we are going to explore property 1 using theorem 14 as sort of our context to help us with this. Now, theorem 14 was the theorem that said what happens when we do row operations on a matrix, what impact that has on the determinant. So I'm going to start out here with just looking at a 3x3 to help us get our, sense of things, and then we'll explore a little bit more. So, and I'm just exploring this, so I'm not going to use formal notation or anything fancy. So let's say I've got a 3x3 matrix. So we've got some, A11, A12, A13, and so on. So we've got some values there. Now, if I were to take Ka, I can get there actually by doing row operations. I could do K row 1. So now I'm going to have K times whatever was there. Then I can do K row 2. So I'm going to get K times whatever was there. And then I can do K times row 3. and we get K times whatever was there. And then this is going to be KA. So in the end, we get KA, because each row has been multiplied by K, after performing these row operations on our matrix A. Now remember, when we do row operations, they have consequences at the end. So in this case, when I multiplied row 1 by K, that means the determinant in the end has to get multiplied by K. Similarly, when I multiplied row 2 by K, in the end, I'm going to have to multiply row 2 by, or the determinant by K. And similarly here, the impact will multiply by K. So the determinant of this matrix that I started out with is going to have determinant of A. But this determinant of the matrix I ended up with is going to be the determinant of A times K times K times K, or K cubed. So this was a 3 by 3 matrix. So we had to do 3 row operations to get to KA. If we had a 4 by 4 matrix, we'd have to do 4 of these row operations. So we'd have K to the 4th times the determinant of A, and so on. So no matter how big your matrix is, you're essentially doing n of those row operations to each row. And that's why we're going to end up with K to the n times the determinant of A. So this isn't quite, a formal proof, but it does kind of give us a sense of how we would go about writing the proof, because we'd have to express this now in terms of an n by n matrix and how we would explore that. So what I would like you to consider is 2 things. Thing 1, how would one go about writing this in a general format for an n by n matrix? And thing 2, could you still prove this property without using those row operations? So in other words, how would you go about showing that the determinant of this matrix is going to be the same as the K to the n times the determinant of this matrix, using like the cofactor definition for determinant? So those are things that I just want you to think about. We're not going to go through them right now, but consider different ways of approaching a proof, right? Thinking about it from 2 different angles and seeing which one might be easier or more possible than the other. But for now, that's enough of this. Let's go ahead and apply some of those properties that we talked about in the previous theorem. Example 50 is a big one. There's going to be 6 parts to it. To help us out, I've listed our properties of determinants on the side that we've been discussing so far, and we're going to apply them to find some determinants. So in this case, M and fancy M are 3 by 3 matrices. We know that the determinant of M is 4, and the determinant of fancy M is -1/2. So the 6 problems we're going to solve are finding the determinant of M times fancy M, finding the determinant of fancy M inverse, determining the determinant of 5M, finding the determinant of the transpose of fancy M, finding the determinant of twice the inverse of M, and finding the determinant of negative fancy M times M transpose. So, as we've done in the past, if you would like to pause the video here and work through those 6 examples, I'm going to get out of the way for a moment. You can copy those down, work them out, and see what you get. And then when you unpause, I'll just speed through them. I'll work through them all. Are you ready? Yay, okay. So for this first one, the determinant of M times fancy M, I'm going to use my second property here to find the determinant of a product. It's the product of the determinants. So this is the determinant of M times the determinant of fancy M. The determinant of M is just 4. And for fancy M, it's -1/2. So we end up with -2. There you go. For this next one, to determine the inverse, we're going to use property 4. The determinant is not 0, so we know it has an inverse. And the inverse's determinant is the reciprocal of the determinant of the matrix. So this is going to be 1 over the determinant of fancy m. Now, the determinant of fancy m is -1/2, so its reciprocal is -2. Not too bad. For part C, to find the determinant of 5m, I need to know the dimensions of m, which so far we haven't had to use. But we're told that m is a 3 by 3 matrix. So here we're going to use property 1, where the determinant of a scalar times a is the scalar to the nth power times the determinant of a. So here, this is going to be 5 cubed times the determinant of m. So 5 cubed is 125, and the determinant of m is 4. So that's going to give us a nice determinant of 500. Don't be dismayed by large or decimal or fractional answers. Our determinant can be any real number, so they can all pop up. For part D, we're finding the determinant of the transpose. This one's really nice because the determinant of the transpose is the same as the determinant of the matrix. So this is the same as the determinant of just fancy m, which is a -1/2. Now for these last two parts, we're actually going to be applying two properties because we have here a scalar multiple and we have an inverse. So to start out with, I'm going to deal with the scalar piece. And the scalar piece is going to be, in this case, 2 cubed. So we're going to get 2 cubed times the determinant of m inverse. But the determinant of m inverse is the same as the reciprocal of the determinant of m. And 2 cubed is 8, so I'm going to do that at the same time. So this is going to give me 8 over the determinant of m, which is 4. And 8 over 4 is 2. There we go. Now, same thing with part F. This one's going to combine 3 properties of determinants here. So you may be wondering what the 3 are. Well, we obviously have a product and we have a transpose. And we also have this multiplying by a -1. So we're going to have to apply this first property here and do -1 to the 3rd power. So I'm going to start out there, -1 to the 3rd power times the determinant of fancy m transpose. Now, -1 to the 3rd power is just -1, so we can just bring down like a negative. And then the determinant of a product is the product of the determinants. And to finish this up, the determinant of the transpose is the same as the determinant of the matrix. So I could write this just as the determinant of m. And now we can fill in our values. So this is -1/2 times 4. Half of 4 is 2. The 2 negatives cancel. So that's it. Here we have 6 examples of applying these determinant properties in a variety of ways. I think we have just one more example. Yep, just one more example for this video, and then we'll be done. We'll wrap it up. So on to example 51. Okay, for example 51, we're going to see if this matrix A is invertible or not. And to do that, we're going to be applying this 4th property here by checking to see if the determinant is 0. So basically all we have to do is find the determinant for matrix A, and if it is 0, then we are not invertible, and if it isn't 0, then we are invertible. So we've explored tons of techniques for finding the determinant, right? You can use the definition, you can use row operations, a variety of properties to see what the determinant of this matrix is going to be. So pause the video here, find the determinant. I'm going to work it out. I think I'm just going to use Laplace expansion, maybe along that 2nd column because it has a 0 and some nice 1s. And then we'll go through and solve it. Okay, so take a moment, pause the video here if you like, and find that determinant. Okay, how did you do? Did you find the determinant okay? So I used cofactor expansion along column 2. It's always nice to indicate which row or column you're using, so someone who's looking at your work, including future you, knows what you did to get there. So going along this column here, I had 0 for the first one because I was going to multiply by 0. And then I took -1 times -1 to the 2 plus 2 times the determinant, the minor, right? And then we have the proper cofactor over here as well, times 1, because we had a 1 here. And when I worked it all out, my math gave me an answer of 0. So hopefully you also got 0 as a determinant. What this means is since the determinant is 0, this matrix is not invertible. So we can't find an inverse for this matrix. So in this video, we've seen already a little bit how determinants and inverses are related, right? So if the determinant is 0, there's no inverse. And if there is an inverse, then its determinant is the reciprocal of the determinant of the matrix. In our next video, we're going to explore in even more depth how we can use determinants, not only to figure out whether or not an inverse exists, but how to find that inverse. So we're going to use an alternate technique to the augmenting of the identity matrix and row reduction. So our alternate technique is going to involve determinants to help us find an inverse. So I'm looking forward to seeing you then. In the meantime, have a wonderful day, and yeah, bye.